First, thank you to the organizers for the invitation. It's my first time in here. It's very exciting to be here. I like your country, so I hope to be back very soon. I myself now working for the Virgo collaboration. I'm from Urbino in Italy. And today I'm going to talk about a very specific problem. However, it's sort of influencing many decisions we have to take with respect to future detectors. This here is, I'm going to talk about Newtonian noise, which is produced by terrestrial gravity fluctuations. And this is a prediction of the Newtonian noise for Advanced LIGO. And you can see here, the reference or design sensitivity of Advanced LIGO at very low frequencies. So here, I'm not just drawing a simple line which would represent the average gravity noise, Newtonian noise. Instead, I'm giving you a full histogram here to tell you, there's also some significant variation of that noise. That is because the underlying source of that noise, in that case, and I will talk about that more soon, is seismic ground vibrations. And so these are highly non-stationary, and this leads to a huge variation. So let's say this level here, on top of this red region, that's kind of the 90th percentile. That means 90% of the time, Newtonian noise will be below this line above that red region. That means 10% of the time, Newtonian noise will be stronger. That means 10% of the time, we may, in the future, be limited, even Advanced LIGO, by terrestrial gravity noise.
Okay. Can I ask just a very naive question?
Yes.
So this is this is only Newtonian noise from the seismic noise?
Yes.
And how do you separate it?
So I will explain this more on later slides. I just wanted to introduce right away the problem and point out some features here. So I will answer your question very soon. What I also want to show is that, in the past, we really didn't have to worry about this. It never showed up. We have never seen Newtonian noise in detectors. And also in O1, we haven't seen Newtonian noise. And to get to this sensitivity may still require some time and improvements. So nonetheless, we may be able to see it in Advanced LIGO in the future and may be able to test some of our models. More importantly, though, this is a noise source relevant for future detectors when we try to improve low-frequency sensitivity even further. And we have already seen some ideas like the Einstein telescope or the Cosmic Explorer. They sort of try to get better low-frequency sensitivities. So let's talk about really what is producing these gravity fluctuations. So the main source we are worried about is seismic Newtonian noise. That means ground vibrations are changing the density in the vicinity of your test masses. This can either be a density change inside the medium produced by compressional seismic waves, or it can be any displacement of the surface or an interface in your medium. So any of this can produce a density change, and that is associated with a gravity change. And so this is really, in the end, in fact, the surface displacement near the test masses is really what produces the dominant Newtonian noise, for example, in Advanced LIGO. And so in reality, if you think about future detectors, you may have to worry about a couple of wave types. We have surface waves, which are Rayleigh and Love waves, or body waves, which are compressional or shear waves. And all of these matter. Not all of them can change the density in the medium, but all of them can sort of produce surface displacement. That means all of these can lead to gravity perturbations. And as I said, Newtonian noise is non-stationary, which makes it especially difficult to deal with. And it is a low-frequency problem relevant only below, even in the far future, below 30 hertz, say. Okay. Something else which is really important Less so for Advanced LIGO because it, as I'm going to show, it's not really relevant. But for the Einstein telescope, for example, atmospheric Newtonian noise is a big issue. And this is, in fact, the only gravity fluctuation that has ever been observed, not by gravitational wave detectors, but by gravimeters at millihertz frequencies. They have this in their data, and they actually found ways to cancel it in their data. I'm going to talk about that as well. So there are different forms of atmospheric perturbations. One is, if you have a quasi-static temperature field, and now this is transported by wind past your test masses, then this will turn into gravity fluctuations again at a specific location. That is one mechanism. The other one is direct density perturbations by, or fluctuations by sound, propagating in the atmosphere or in the laboratory buildings. And our understanding of this is very, very poor. I mean, we have some analytic models, but they are highly simplified. Turbulence in general makes this very difficult to understand and to model, and we have still a lot to do in, to get better estimates, and then in the end come up with ideas how to mitigate this form of noise. Okay, now like a more detailed view of gravity noise budget for Advanced LIGO. So here again the Advanced LIGO reference sensitivity, and the green and blue curves here are the seismic Newtonian noise for the two sides. And I was drawing here the 90th percentiles. But we investigated a couple of other potential contributions. For example, the black one here is a sound in the laboratory buildings and what the gravity perturbations of that. Then we looked at fans, vibration of a nearby fan, ventilation fan. Buildings may rock back and forth, and wall panels may shake. So, you know, we constructed a noise budget from this. But you can see by quite some margin the seismic Newtonian noise. In this case, it's really the surface displacement is what dominates the gravity perturbations, and that's well, we can, you know, this is all based on models. Obviously, I mean, we want to measure that. I mean, this is all, you know, based on some simplified models, how we measured, let's say, vibrations throughout the LIGO buildings, and we turned that, you know, using some model into these curves. Okay? We are not yet able to measure transfer functions. Okay, so now back to the question that I raised really in this, with the title of my presentation: how can Newtonian noise influence the detector design? You know, whenever there is something that influences the detector design, it means that we can do something about it. We can do something about Newtonian noise. That's what it means. And so there are various ways we can do something about Newtonian noise. So the first one is site selection. So that is a process that you just went through in India, and you know, you are looking for sites that are, you know, especially low in seismic noise. And in the future, you also want to search for something, you know, if you think about large third-generation detectors like Einstein telescope, you look for some site with low atmospheric noise, for example. Then, you know, you could consider in this context to go underground. That's typically far more expensive, but has some advantages. You could consider to, you know, you have infrastructure that is producing seismic noise at your site. So you can think, can we somehow suppress the seismic noise produced by this infrastructure? Ventilation fans, for example, produce dominant seismic noise in the Newtonian noise band at the LIGO sites, at least at some of the stations. We know this for sure. So you may wonder, okay, can we maybe build these ventilation fans further greater distances to the test masses, and thereby lower seismic noise and therefore Newtonian noise. Then some more exotic idea is to build shields or recesses to lower Newtonian noise. Now, you can obviously not have a shield directly against gravity fluctuations, but what you can do is you can have a shield against seismic noise or against atmospheric noise, and in that way suppress your gravity fluctuations associated with that. I will go through that list again with some slides to give some more details of these ideas. And then something that we follow as the, let's say, most immediate way to deal with Newtonian noise is Newtonian noise cancellation. And I'm, in fact, collaborating also with a group, with Sanjit's group at IUCAA on this problem. So the idea is that you can monitor the sources that produce your gravity fluctuations with an array of sensors. And so then you use the data from these sensors to produce a coherent estimate of your gravity noise associated with that. And typically, one way to translate your sensor data into an estimate of the gravity fluctuations would be to use Wiener filters. And then you can cancel and you subtract that estimate from your data. And that way you suppress Newtonian noise. Related to that, you may reconsider the site selection problem, not only to search for sites that are low in seismic noise and low in atmospheric noise, but also which are flat to facilitate noise cancellation. Because if it's a very rough surface, you would have a lot of scattering of seismic waves. That would make this problem a little bit harder. But that's really an advanced aspect of all of that, and to be considered least of all of this, I would say. Okay, let's go through this quite exotic way to suppress Newtonian noise, which only works for surface sites, really. So you can build shields. For example, against atmospheric Newtonian noise, the idea could be that around your end stations, here for a triangular detector, you could build huge domes with a radius of maybe 100, 200 meters. Just give numbers here. And in that way, you would have no air currents inside these domes, say, and that means all of the gravity perturbations associated with a temperature, with a quasi-static temperature field that is then, cannot be transported past your test masses anymore. So that contribution would be fully gone. And this would also allow you to cancel very efficiently infrasound Newtonian noise, because you could hang from the ceiling many microphones. So you could have a three-dimensional monitoring of the volume in your dome, and you would cancel all your infrasound Newtonian noise. So this would be very good against infrasound Newtonian noise. Against seismic Newtonian noise, there are two schemes proposed in the past by a long time already ago with one of the first Newtonian noise papers by Kip Thorne and Scott Hughes. They proposed modes. So you would dig modes around your test masses deep enough so that the surface waves incident would be reflected again from the modes. And so you would have a quiet zone inside here. That is a quite nice idea. I'm a little bit worried that, the point is it assumes that the seismic noise comes from the outside. But I think that's not really true for the LIGO infrastructure, where you have the sources quite close to the test masses. So that scheme doesn't work in that case anymore. Something that would work even in that case is to dig recess around your test masses. These are huge holes, 5 meters deep, with this horizontal geometry. And the geometry is chosen to maximally suppress Newtonian noise from surface waves. That is kind of, let's say, feasible, something that you might consider, but obviously also quite a huge impact on the infrastructure. And there are many aspects not investigated. But what we can at least say, if you did have such a recess, then you could achieve like a factor 4 or 5 suppression of Newtonian noise from these surface waves. And again, it is a kind of complicated problem, and we couldn't investigate this in detail in all aspects. For example, the recess would also cause scattering of seismic waves, so that we didn't take into account in this simulation. And also, you may have some, you have to leave a central pillar here for the chamber to carry the chamber. And so here, the fact that this is going up again here is really the contribution from the central pillar, the seismic vibrations of the central pillar. They may actually be lower than we assumed here because seismic vibrations really don't find a way anymore to enter the central pillar, and there may be some suppression. So in any case, some aspects that we didn't really look at, but it may be promising. Something to look at in detail maybe. For underground sites, okay, we have Kagra already. Then in the future for the Einstein telescope, we foresee an underground construction. Obviously, so the main motivation is really because of the gravity noise, to have a detector underground. And there's a reduction of seismic Newtonian noise because it is, the dominant contribution, not only at Advanced LIGO, but also at most other sites in the world. The dominant contribution at a surface detector is from surface seismic waves. And that contribution gets suppressed when you go underground. Then there is another contribution left from body waves, and that doesn't change if you go underground, but that is really a substantial factor weaker than the surface Newtonian noise. And then obviously, since you create some distance between test masses and atmosphere, you also suppress gravity noise from the atmosphere. Okay. Now, for the Einstein telescope, people looked at various sites, underground sites. This is, for example, seismic spectra measured, say, between 0.1 hertz and 10 hertz. And here, ground acceleration. And you can see, for example, here the spectrum of the Virgo detector. It's really loud, very, very loud. And also here, in this case, mostly produced by the site infrastructure. But at the surface, it's always going to be louder unless you're really searching for very quiet sites, which you may find in Antarctica or some places in Alaska or whatever. Underground, however, you are having much smaller, weaker seismic spectra. And here is the level that you would need for the Einstein telescope so that if you go underground, you don't have to do any more cancellation of Newtonian noise. So that means if you measured seismic noise at this level at some site, then you don't have to do any Newtonian noise cancellation anymore. What you can see is for the typical underground site, you still end up with some factor that you may want to suppress with sensor arrays, as I'm going to explain. Okay. Then let's look at some other seismic Newtonian noise spectra. So here I'm splitting contributions in surface and body waves. So the body wave Newtonian noise is weaker by a factor 1,000, 100,000. It really, 100 to 1,000. It really depends on the sites that you consider. So you are getting, by going underground, you are getting rid of this surface contribution, and then you are left over with this body wave contribution, as you can see in the right plot, where I have spectra here for two different depths, 100 meter and 300 meter depth. So these are the corresponding surface Newtonian noise spectra, and here it's an almost unchanged contribution from the body waves. Okay, and that you still have to deal with even if you go underground. For the atmospheric Newtonian noise, here you see, my modeling gets very simple in this case. We really don't understand so much about this yet. But we roughly know at which frequencies this appears. Temperature Newtonian noise with a 20 meters per second airflow. At the surface, that means you have still some distance between test mass and that source here because of the buildings around the test masses. So in that case, the Newtonian noise would be that line, which is very steep, but it doesn't really go beyond a couple of hertz, 6, 7 hertz. And then if you go 100 meters underground, you would have a very strong suppression. It would be shifted to below 1 hertz. So you completely get rid of that Newtonian noise by going underground. Or equivalently, if you had a 100-meter dome, you would have the same effect. Infrasound Newtonian noise, it doesn't go away that quickly, but sufficiently at least for the Einstein telescope, where the surface line is really going into this 100-meter underground line, so below other instrumental noise. Okay, so now another aspect of site selection, as I already mentioned, is seismic scattering. So you want really, if possible, you know, if we are talking about the ideal site from the science perspective, then it would be, and we don't worry about money really, then it would be an underground site with a flat surface. So if you don't have, you know, if you have a flat surface, then even in that case, there's some scattering going on of seismic waves. For example, an incident compressional wave, which is the longitudinal seismic wave, would be converted partially into shear waves to fulfill some stress boundary conditions here. But if you have a rough surface, then scattering gets very, very, very complicated, and you have coupling between all wave types. And if you now want to understand the seismic field to design a Newtonian noise cancellation system, that will be very, very difficult. We have done some studies of specific sites. So, for example, if you are in Montana in the mountains somehow, where elevation change can be a kilometer, then you would have really a lot of seismic scattering, and we showed quantitatively in that case, you would really be in trouble if you now want to understand that seismic field, monitor it with seismic sensors and cancel Newtonian noise. And we also studied some other sites for effects of surface topography on seismic fields. For example, a quantity that I will show later again for the LIGO site is correlation between seismic sensors. That's really, if you ever want to start designing a Newtonian noise cancellation system for your detector, and the first thing what you would do is you would deploy seismic arrays at the site, and you would look at correlations between all of your seismic sensors. And that is all you need to design a Newtonian noise cancellation system. I will come back to this. So for that reason, we have looked at correlation functions at some sites in the world, and here there was also some elevation change in Texas. There happened to be an array, not our, other people, geologists, geophysicists deployed it there. And so the elevation change could somehow be linked to structure in your correlations between sensors. So if they happen to be separated along this direction, then you can see like local maxima of correlation. And in this direction, however, there's no such, there are not these local maxima. So you can see there's some influence of topography on correlations, and therefore also on your Newtonian noise cancellation here. So let's get to Newtonian noise cancellation. This was an image that was produced by a student at IUCA. And what he did was the following. So the way it worked, as I said, is you would have test masses here in these locations, and you have sensor arrays, in this case seismic arrays, around your test masses. And now, obviously, the question is where, you know, if you have some number of sensors, where would you really put these sensors so that you learn everything you need to learn about the seismic field and then produce the best estimate for your gravity noise. And so here you can see the optimal configuration of using 6 sensors for one of the N test masses, assuming that seismic waves in average come from all directions, essentially. So isotropic field, and at least in the, you know, in the 2D sense, so it's, we are worried about the surface waves only. As I'm going to show, this is not really true. We don't have isotropic fields, but this calculation was done for an isotropic field. The same here, so the same result here. And here you see, here the optimal arrays look a little bit different because these sensors are used, you know, not only for one test mass, but they are always used for 2 test masses and Newtonian noise in 2 orthogonal directions. So that is why the optimal array configuration here looks a little bit different. So this was done with a simulated annealing algorithm, and you know, we could also apply this to more realistic models of the seismic field. That's not a problem at this point anymore. Here is one measurement we did with a seismometer array in 2012 at the Hanford site. This was what we observed for the seismic correlations between our sensors. So at 15 Hertz, that is how coherence looked like. So normalized correlation between -1 and 1. And now you know, you can compare this with a plane wave, an anisotropic plane wave model. So this model here or the model of the field that produces this correlation map here is seismic waves predominantly coming from a certain direction. So, and we identified the source really that produces the seismic waves at the LIGO Hanford site at the end station with the ventilation fan. So, and this doesn't change over time. This always looks like that, basically always, unless you have a car that makes a transient in the seismic noise for some time, but most of the time it looks like that. So that is very good because the fact that we can model this quite precisely by a plane wave, an isotropic plane wave model, tells us that once we have a Newtonian noise cancellation system installed there, it will be extremely effective. As soon, whenever plane wave models are giving us, can, you know, give us good matches with observation, we know that Newtonian noise cancellation will be extremely effective. When, so the question is, when do plane wave models not really approximate reality very well? This is when you have strong local sources, and by local I mean really close to the test masses. This could also be seismic scattering. So the good news here means is that all the sources we have, even the infrastructure at LIGO, is sufficiently far away for plane wave models to be more or less accurate, and also we have no significant seismic scattering really. However, if you look at this very closely, it's not a perfect match. So we don't really have what we would call a homogeneous seismic field. It's an inhomogeneous seismic field. And these details may in the end matter, so we have to look at this to understand you know, limitations of our Newtonian noise cancellation. But I mean, we can be quite optimistic at least to get significant suppression of seismic noise, Newtonian noise. I already said that the student from IUCAA did array optimization. And this is really how important it is. So here you see suppression factors of Newtonian noise as a function of frequency using seismic sensors. And here you have different seismic arrays deployed. We have calculated these residuals for different seismic arrays. For example, a spiral with 20 seismometers and an outer radius of 7 meters. A spiral with 6 seismometers and a radius of 7 meters. And then the optimal array configuration with 6 seismometers optimized for the specific frequency 10 hertz. And so compare the residuals. So first of all, if you compare the two 6 seismometer configurations, the optimal one really produces far lower residuals than the spiral. So this makes really a huge difference, and it's clear we need something like optimization. Low residuals like this with a spiral can only be achieved if you really increase the number to 20 of the seismometers. So that really tells you that is something important to do. This is for the surface waves, for the surface Rayleigh waves. We don't really know yet how to do this for body waves, so we have not solved this problem yet, for example, for the Einstein telescope. That's still work that we need to do. Something else that we may consider, I mentioned this here already in the list, we are always assuming that the sensors we use monitor vertical displacement of the surface. But there are other seismic sensors like tilt meters, strain meters, and even dilatometers could in principle be used. None of these yet have been developed for the Newtonian noise band, but people tell me that at least for tilt meters this would be an option. We could do this. We could have tilt meters. And it turns out that tilt meters are the closest we can have to mimic the gravity signal. So what do I mean with that? If all seismic sources were distant so that we can approximate all seismic waves as plane waves, then the tiltmeter signal would be an exact copy of the gravity noise signal. What that means is you only need one tiltmeter to do cancellation. In this case, in this ideal case, you would only need one tiltmeter and you can cancel all of your seismic noise from that test mass. So if you have 4 test masses, you would need 4 tiltmeters. So that would be a big advantage, obviously. And it is, we are currently writing a paper to see what the limitations of that is in case that we don't only have plane waves, but we have some scattering or effects like that. Right. Now, a tilt meter, for example, that's like the model developed currently by Krishna at Washington, in Washington State, and another option would be to use strain meters, which would operate more or less like that, where you measure the distance between 2 points attached to the ground by a laser, let's say. And the strain meter has a similar role as a tilt meter has for surface. So the tilt meter is the best imitation of Rayleigh Newtonian noise in large-scale gravitational wave detectors, while the strain meter is the best imitation of body wave Newtonian noise in gravity gradiometers. And a gravity gradiometer is simply, what I mean by that is a very, very short gravity strain meter, something which is so short that you are essentially measuring the gradient of gravity fluctuations. In that case, you could do body wave Newtonian noise cancellation very efficiently with a seismic strain meter. The same story as the tilt meter for Rayleigh Newtonian noise. So I think it is really interesting to look into these instruments more carefully and analyze the problems more carefully. So I'm coming to the end now. So I've one slide again summarizing a little bit the constraints on observatory designs. For the surface, you would have the option to improve the design of laboratory infrastructure to move away sources of seismic noise as far as possible. And you could consider like exotic techniques like constructing domes as shields against atmospheric Newtonian noise or recessed structure as I showed. Then something that I think Rana really started to discuss as an option for a future detector would be to have, instead of having the domes, you could search for a site where these domes occur naturally. That means you stick the ends into mountains. You don't have to stick them very far, like, only a few hundred meters, but you don't have to construct all of the detector underground. That would already provide the very important suppression of atmospheric Newtonian noise and really save some cost. And that is really, I think, a very elegant idea. The only kind of complexity coming with that is that necessarily you would be in a non-flat topography anymore, and you would have seismic scattering, and that would, if you ever tried Newtonian noise cancellation, then you would have a little bit more difficulties with that. Underground, the only, once you make a decision to go underground, the main question is really how does infrastructure elevate underground seismic noise? Because many people say like, okay, underground seismicity is very low, so we build our detector underground, but you have to be very careful that because the LIGO sites produce most of the seismic noise at the LIGO site, so is the Einstein telescope producing the same level of seismic noise underground? If that is true, then obviously you wouldn't go underground anymore, or you would be working very hard on solving this infrastructure problem with seismic sources brought in by building the detector. So it's that's something that we haven't really investigated yet quantitatively. It's but I think Kagra will already give us some idea how much they elevate seismic noise underground with their infrastructure. And to give some ideas of what we are doing or want to do in the near future or distant future. So we have groups working on seismometer development. So it's not really at the moment not so important. The seismometers we need for the LIGO detectors to do Newtonian noise cancellation, they are very low cost. So there's no need yet, but this is already being done for something like Einstein telescope, where you want to have a low cost seismometer that is sensitive even at low frequencies and in low noise environments. We are currently, as I explained, we are investigating seismic correlations. One example is also an underground site in the US, the former Homestake mine where seismic fields are investigated or analyzed in terms of wave composition, body waves, Rayleigh waves, and so on. Something similar to what we do already at the LIGO sites as well. Then in the near future, we should theoretically first of all analyze the gain from alternative sensors, and then really encourage people to build these if they are useful. We want to have hydrodynamical simulations of the atmosphere and calculate really gravity perturbations, and then also that would tell us how we could possibly cancel Newtonian noise from the atmosphere if there's something similar we could do. As for the seismic Newtonian noise, yeah, we still have to look for or understand optimization of seismic arrays for underground sites. That's also a quite difficult problem. For the distant future, how would you possibly monitor the atmosphere so that you have the information to cancel Newtonian noise from the atmosphere? You cannot, you know, the only atmospheric sensor that we really know of is microphones, and you can only deploy them at the surface. You cannot deploy them high up in the air easily. But there's something else that is really not applicable yet for this problem, but something that may be an option in the future is something like these LIDAR systems, laser monitoring, you know, systems that can actually do atmospheric topography, where you would have many lasers shooting into your atmosphere, and then you see what's coming back, and you would be able to see density perturbations, temperature perturbations, and so on of the atmosphere. And that may be turned into a cancellation system for atmospheric Newtonian noise, maybe. But that is really distant future, and yeah, and that's all I wanted to say. Thanks.
I was wondering about the seismic noise. Does a type of soil or a type of rock that you build on make a difference? And is there a way you can justify it like that?
So, yes. For the gravity noise, it's a little bit more tricky. But in general, what you have is if the soil is very hard, then if you have a source producing seismic noise, then the amplitude of that noise will be smaller if it's hard, and you will produce a higher amplitude of seismic noise if the soil is soft. So in that case, you could say hard soil has an advantage because it comes with smaller seismic noise. However, the density will also be higher of that hard soil. So that means there's a trade-off. You have to be careful because the density is another, you factor that in another time for the gravity noise. So even though you may have lower seismic noise, you will have a boost of gravity noise because of the higher density. And so you have to be a bit more careful if you really gain by harder soil. But my guess is probably harder soil is always advantageous in the end, even if you factor in the increased density.
Yeah, and so how does this dilatometers work? What are they?
This? No.
Dilatometers.
The dilatometers. Yes, so dilatometers are really measuring a change in volume of a rock volume, of an element, volume element. Typically, these are really very, very low frequency sensors, the way they're applied. And so I didn't really mention them because I think to develop a version that measures at very high frequency is challenging, but in the end, you could always construct it from strain meters and tilt meters because the change in volume, you can, if you monitor strain in all three directions in the end, you can also get that volume change out of that. So, so I guess it's probably the strategy would be to have more strain meters instead of a dilatometer.
You mentioned some prescriptions which result from all this work for sites. I was wondering if they're also evolved into some sort of protocols of tests for site selection, for example, to pick between competing sites or something like that?
Yeah, we have, well, it's, yeah, we have such, I wouldn't call it protocols, it's not that official, but we have sort of set up lists like how you would evaluate the site and what the priorities are. I mean, in the end, it should really, for anything that we are, worried about in the next 15 years, say, or 20, really the main point is low seismic noise in the Newtonian noise band. That's it, basically. You shouldn't worry about anything else. The others are things that are lower priority, not only because we start to worry about them later, but also maybe because we can do something, even if we didn't pick the best site, we may find alternative solutions to deal with that. But low seismic noise is really like the huge advantage you get from site selection.
Question. So you measure this effect of fans and those and all. Are they measured with the seismometers or?
Yeah, I mean, you can, yes. I mean, you know, technically people wouldn't call all these sensors seismometers, but you can either have measure strong vibration directly on the fan, or you could then at some distance to the fan measure the ground motion produced by the fan. So I think all of this happened really. We did all of this. But yeah, it's always some kind of vibration. Of course, the fan can also couple in another way, because you have not only small amplitude vibrations, but you have also the rotation of the fan itself, macroscopic motion, and that happens at specific frequencies, of course, the gravity perturbation. But we also estimated that, and we found this, you know, if you have it 5 meters away from the test masses, to be negligible. But that's another aspect of the fan gravity noise that you could be worried about.
But I thought fans always produce a higher frequency effects rather than what you show in the millihertz and so on. How does that happen?
Well, okay, so I mean, we are really, I mean, for advanced LIGO, say, we are worried about 10 to 20 hertz. And the rotation frequency is not that far off from that. But the point is, really the seismic noise is not produced, you know, the seismic noise is produced by little asymmetries in your fan. And that produces, in the end, vibrations at all kinds of frequencies. So it's not really, you know, the fundamental rotation that you see in the seismic noise, but it's a broadband spectrum because of asymmetries in your fan in the end.
You had mentioned that for Newtonian noise cancellation.
Where are you?
Yeah. Okay. So you mentioned that for Newtonian noise cancellation, you could use sensor arrays for which you had to model the different sources and characterize them. And you also mentioned that one of the noises from atmospheric Newtonian noise comes from turbulence. So how would you model turbulence?
Yeah, turbulence, that's very difficult. So the models that we currently have take turbulence into account in one specific way. So I told about this temperature, quasi-static temperature field that gets affected. This temperature field at high enough frequencies is really produced by turbulent mixing. So it produces a very characteristic spectrum of the temperature perturbations. So in that way, we have temperature already, turbulence included in the models. But really what worries us is that we don't have a laminar flow in the end of air, but we have surface structure, and that will cause turbulence at specific scales. So for example, if you have a building of a specific dimension, you will have turbulences, you will have characteristic frequencies in your streamlines, in the motion of your air. And so this is something, so all I can really think of, I mean, people try to make some analytic modeling of that, but all I can really think of is we have some kind of numerical simulation that can somehow handle turbulence to some degree, and we get, yeah, I really don't know. I really don't know at this point, but we need experts, and I'm not an expert on this. We need somebody who knows how to do hydrodynamic simulations of the atmosphere and to model turbulence. Once you have turbulence modeled, to get out the gravity perturbation from that is rather easy. So we just need the atmospheric modeling, really.
Any more questions? Okay, let's thank speaker once again.